Hello. So just want to make sure everyone can hear me clearly because my Wi-Fi has some problem and I have to use a mobile network.
Yes, you look good
Thank
on
you.
the camera. There you go.
Thank you. Let me share the step two. Yeah, hope it now is coming back. Yeah, the mobile network sounds good. And let's begin. I hope it's the bandwidth is not too low. Okay, we can. It's a little bit slow. It takes some while to just load this page. Let me see. So we are. Okay, so last time we talked about the domain name system, right? So so that you can go ahead with the quiz, and that's the last quiz we have for this semester. And this week is the last week of the class, right? So, and the next Thursday and Friday we'll have final exam. On this Friday we will have a walkthrough of the a few slides, review what we could be testing you in the final exam. Okay. And the final exam will be in the form of a relatively flexible timed quiz, which means we still have 2-hour limit. And if you have need a special accommodation, like with DSS, right? So just remind me, send an email. I will adjust the time. Okay. So base time is 2 hours. Okay, but you may use more than that, right? If you have the permission from for special accommodation. And again, so there's no more time conflict, right? Because we have 2 days, okay, that you can choose anytime you begin, okay? So the exam will be open on Thursday, the Thursday of the next week, okay, not this week, right? And Thursday, Friday, 2 days, right? And it will all be like 40 to 50 multiple choice questions, right? Because we want to finalize all the grades by the Monday after that exam week. And we might not have time if we test like more too many questions that are not multiple choice. Okay, but you potentially need to derive all those answers yourself on a scratch paper, and then you select the correct answer. Okay, among those multiple answers. All right, so let's go back to where we were left over last time about the route assisted congestion control, right? So we were talking about transport layer. We have so transport end to end, right? So you are not aware of anything in the middle, but the congestion really happens in a intermediate bottleneck link between 2 routers that are having too many streams. Okay, so we want the router to have some built-in support. The reason very simple is think about not everyone is running TCP, right? Some people can run UDP, and if that person running UDP is not back off when there's a packet loss, right? A packet loss, and what will happen is that so that UDP will keep causing congestion, and if other TCP connections back off, then the UDP will just utilize, occupy more bandwidth. Okay, that breaks the fairness requirement. Okay, so to overcome these limitations, we need a router support, right? So last time we talked about the you see here, this flow is unbalanced. Maybe this one is more aggressive, like UDP, and keep increasing the bandwidth. This one may be more, less aggressive, back off periodic. And there's another problem, right? So this is unfairness. There's also flow synchronization, which means everyone back off, right? At a point where they detect some packet loss, okay? And then they slowly increase. And during this slow increasing period of time, the bandwidth is not fully utilized, okay? And when your bandwidth is almost full, what will happen is that delay will be very long because we want to over budget our bandwidth. If your bandwidth is almost 100%, the delay will be infinity. Okay. So last time we talked about the RAD solution, random early detection, which means we don't want to wait till the very end moment where there's no space in a router's queue. Okay. We want to drop some packets way earlier than you become full. Okay. So maybe when it's already quite close to full, we start to drop. Okay. Because when you drop some packets, the benefit is that that TCP connection will detect that and it will back off right early. Right? So if you random drop early, that TCP connection can adjust the speed early without totally run out of the buffer of the router. Okay. Again, this is still using the first in first out scheduling. Okay, and it replaces the job tail buffer management where you just keep appending packets of no matter where the stream is from. Right? So. And then when the buffer is full, you just drop whatever coming when the queue is full. Okay. So here we are probabilistically discard packets, right? And so even before the packet queue become full at the router, you will still drop some packets. Okay. But the probability is computed as a function of queue length, right? If your queue length is long, right, almost full, then you should drop a packet with higher probability. Okay. If your queue is quite empty, then you don't even need to drop a packet sometimes, right? So why we are using the average length? Last time we discussed, right? Because there could be some transit change of the suddenly there's a surge of the packet, but immediately it recurs, right? Goes back, right? And you don't want such a transit congestion to cause a lot of overreaction. Okay, so we'll smooth it over some sliding window. So this is the average equivalence. Okay. So there are three RAD variables. Okay, random early detection variables. Okay. The first is called the minimum threshold. Right. So this is like if you look at a queue, right, this is probably where it's still quite empty. Right. If less than mean threshold, then we don't even drop any packets. Okay. On the other hand, if we reach the maximum threshold, right, then we definitely need to drop packets because it's made the maximum all the capacity of the queue. Okay, but in between min and max, right, where smaller than min we don't drop any packets, larger than max we always drop packets. But in between we should still start to drop some packets, but we want to make it a stochastic process, right? So we will flip a coin and then say, hey, whether we want to drop packets, right? Of course, the closer to the max, right? When it's closer to reach the capacity of the queue, the more likely you will drop a packet. You will increase the probability threshold, right? But again, so you will not make it really one, right? Because you still wanna something to go through. So the peak here, the probability peak is probably like 30% or something, right? So you will not just totally cut out that stream as long as there's still some capacity before max. Okay, but you wanna increase the probability drop as your queue becomes more full. Okay, and another concept is how we compute the average queue length, right? So this is the queue length at the current time step, and then you have a smooth queue length before, right? So previous time step you have a already average, right? So this is a moving average, okay, exponential decay moving average, right? And then your current length will play a part in this average, but it will only play a part of weight W. Okay, it will not occupy. It will not suddenly just change to the length. Like you suddenly have a lot of packets, it becomes full, right? So then you will not immediately suddenly drop packets with very high probability. Right? So as long as you can go back to mean very quickly, then you probably will not overreact. Okay. So here's the operation we just mentioned, right? So if your average length that you maintain, right, by the running average, okay, if it's smaller than the mean, right, threshold mean of the queue length, then you always include a packet. Okay, if it's larger than the maximum allowed capacity, then you always drop a packet. Okay, so these are like a regular ones. The interesting part is that in between min and max, where you kind of have quite some packets, but it's not full, right? Then you will enqueue packet with probability P, which means you will drop a packet, right? You will discard a packet with some probability, okay? Right. And by dropping some packet, let me plot something, okay? Maybe in this, in here you have 3 streams, right? You have stream 1, stream 2, stream 3, right? And it happens that because now it's very close to the Q capacity, then this stream is dropped. And when you drop this, right, so this sending speed will immediately cut by half, right, according to our TCP right now, right? What others are lucky and not drop, right? So, and then next time, maybe this guy will flip a coin and decide, hey, I want to drop my sending speed, right? So this avoids a synchronization issue, right? So maybe this goes down peak, and then the other one, this one will then here go down by half. Okay, so you can see that when you are reducing the bandwidth suddenly, right? So this is still using. Okay, so you don't have the synchronized, cut off the band the utilization. Okay, so here are the 3 states. 1 is less than min. 2 is actually Q is full. 3 is actually in between min and max, right? It's getting closer to full, but there's still space. Okay? So how do we calculate a dropping probability P, right? So again, as I said, we don't want to, when it's become very close to full, we still want some stream to get through with low probabilities, right? So we don't want to make the max probability to be 1, right? Which means you always drop it, right? So there will be a maximum probability, which may be maybe 40% or 30%, okay, right? And then this is a linear function, which you can say, hey, what's the current position compared with mean, and what's your max to mean, right? You compute the ratio, which is the probability increase, but you increase all at most to max, okay? And the improvement, so let me see. So here we have another improvement, okay? So we want to spread the drops, right? So we actually use the drop probability P prime, which is P divided by 1. This is P, original compute P. We still divide by 1 minus count times P, okay? So here count is the number of packets consecutively in queue since the last drop, right? So the reason we want to do this is because, we want to spread the drops, okay? If you have some packets consecutively in queue, right? And so this is basically what we want to say. So this Q is the job probability for a particular stream. Let me see. Yeah. So let's say we have this stream, but we have 3 flows coming because we have this channel link. Okay. Right. So let's say this guy has lots of consecutive compacts coming, right? So then you probably this count will be large, right? Maybe 3 come in a row. Okay. Then you wanna. So when this increases, the numerator decreases, right? The numerator decreases, which means the probability of this will increase, right? So compared with this one that, there's packets in queue like not consecutive, right? This consecutive in queue, which means it's really occupying a lot of bandwidth, right? And the 3 times this, and then 1 queue count, 1 packet here, and that's 3 this, and this thing should back off more aggressively. So we will increase the probability of this compared with like 1 at a time. Okay, so we will have this factor to adjust. So let's take a look at a animation for this. So here, let's assume this is the Q length, right? And ideally, we don't allow to go beyond the max, right? So, and we always allow to go in Q when the capacity min. But in between here, we will drop. Okay, so let's take a look at what's happening here. We have a stream where the packets are relatively large, right? By this time, we already reached max, okay? But let's say here, we flip a coin, we decide, hey, we should drop it, right? So we drop it, and then we can have some other packets from another stream, which is gray, okay? And this stream actually is having smaller packets, right? So it can fit in this. So this way it can, better absorb packet bursts, okay? Because let me see. So you can see that if you suddenly have a packet burst, right? So like here, right? It consecutive, immediately will drop this. then this blue stream will start to back off, okay? And then this gray stream can still go through and utilize the rest of the bandwidth, right? So if you have sudden bursts, this can handle. And it avoids TCP flow synchronization because you think about the blue stream, because they have a packet loss, right? So it's already back off, right? Cut the sending speed by half, or hammer to 0 or to 1, okay? Window side to 1. But the gray stream can continue to send, right? Okay. And this avoids TCP synchronization because the gray stream has no packet loss so far. Right? If it has another one, of course, it's go beyond the max. Will kind of shrink its window. Okay. But so far, blue one shrinks the window, but the gray one, it will get acknowledgement. It will still increase the window. Right? So there's no synchronized window shrinking. Okay, that cause bandwidth anti-utilization. Right? And it also signals the end system earlier. Right? So for example, here, even though you have not go beyond the max, this packet drop already signals, hey, it's almost full. Right? So then you will not cause another blue packet count. Right? So this saves an additional effort. Okay, it allows the system to adjust the speed of the blue flow earlier. So this is actually widely implemented on modern routers. Okay. So here's an example where we have the red router with 2 TCP flows. And this diagram is compared to this diagram, okay, where you have unfairness and you have the flow synchronization. Right? So here you can see this is much better. Right? So they kind of use the same bandwidth. Right? So as time goes by, they increase like linearly, right? Not one increase faster than the other. Right? So here's this is a cumulative packet sequence. Right? As time goes by, you send more stuff, but the speed is kind of it's a fair share. Right? Okay, the blue curve will finally catch up and reach the fair point. Okay? And if you look at the the window size, right? So the number of packets, right? So you can see the window size are actually more better utilized, right? So you have synchronization. Right? So this goes down, but this is still increasing, and you don't have the synchronized issue that cause the bandwidth to go down. Okay, periodically going. But this is there any problem with the wrap? Yes, there's still some problem. Right? So there's no protection. Okay. So basically, you think about it, we can have UDP, right? UDP will not politely back off. Right? So because the congestion control is only used by TCP. Okay. But UDP when it has a packet drop, it's just like a loser frame in your YouTube video. It's fine. The server can just keep sending the later frame. Okay. So what will happen is, hey, when when the so basically in our previous assumption, we are assuming that if you have this packet loss, right? So the blue flow will start to adjust the speed. Okay? But UDP, you don't have to adjust the speed, right? You can abuse it, right? So then you keep increasing, even you have most of the packet drop, right? You keep sending stuff, okay? And this will cause, most of the bandwidth be occupied by the UDP, right? And you almost have very few for the TCP connection, even though you have like 31 TCP connection, right? So this can affect the performance of other flows. So the problem is that this is a stateless solution, right? So the red is stateless, right? So it doesn't really care about which flow it is from. Okay, I just take a packet, and if it's within min max, then I based on the queue length, I will flip a coin and drop a packet randomly. Okay. So ideally, we want to maintain the states, right? Let's say, hey, we have 32 streams, right? Send connections, right? And none of them can use more than certain fraction, right? You should allow others to also use the bandwidth. Okay? So a ideal way is to maintain one queue per flow, right? So this means we can do a round robin manner of different flows. Okay? For example, for the blue flow and orange flow, we have this, and then blue flow, this blue flow, if by this time blue flow is sending too fast, it utilizes all the queue of the blue flow, right? So next we should So here's the speed, right? So here's the idea, okay? If you have the packets coming, okay, we should send this packet, right? And by this time, we should not keep sending this blue flow. We should allow other people also to send, okay? Right? Even if you have more, right? So you will not occupy other people's share of the queue space, okay? This will be jump, and this blue flow will be not abuse the bandwidth, right? If it's UDP, it's fine, right? So if your queue is exhausted, you don't occupy other people's bandwidth, okay? So this requires a state, right? You basically need to remember what's the IP address of the two end systems and what's their IP ports, okay? So it provides some protection and isolation between different flows, okay? But there's a problem with the round robin approach, okay? So there's a bias towards flows with large packets, because previously, this example, we think packets are of the same size, right? But in reality, the packets can have different sizes, right? So for different applications, maybe some application you just do some simple verification message, while others you are sending big files, okay? So a lot of packets, okay? So this will cause some problem because it will be biased towards large packets, right? Because the queue is counting how many packets you have, right? Not counting how many bytes, okay? So you send this, and you send this, and then you send another packet, right? If you look at the bandwidth, actually the blue one is utilizing maybe 4 times. Let's assume the packet size is different by 4, okay? The blue stream is utilizing more bandwidth, okay? So another complexity is that you must keep track of the number of flows, right? How many different pairs of key value pairs? No, not here. So the IP pairs and port pairs, right? And then for each flow, you should maintain a queue, right? And make sure it's not abusing the space. Okay. So it must also maintain, you need to maintain the state, right? Which means the flow to queue mapping, right? If you go from IP1 to IP4, IP1 to IP2, with this ABC port to DEF port, you should always go to this queue, not the other. Right? So these mappings also need to maintain at the router side, which we know it's not a realistic because router is stateless. Right? It's just look at the packet and stuff. Right? So you don't want a per flow state in the router. Okay. So is there any solution? So firstly, we want a so-called bit-by-bit round robin, which means I don't just count the number of packets. I count in the unit bits, right? So if the number of bits in the blue packet is 4 times that of the gray bit, right? So I should, when I send one blue packet, I should, in the meanwhile, send 4 gray packets, right? To make the bandwidth even, right? All right, so this is the bit-by-bit round robin, which addresses the first concern about packet size difference. The second, the question to ask is whether you can do this in practice. The answer is no, right? So the packets are the minimum unit of transmission by routers, right? Because you check the headers, you get the IP address, and you decide where you put to, right? So packets cannot be sliced into bit-sized pieces, right? Packets need to arrive with headers intact, okay? And so even if fragmented packet has overhead, it will need to attach multiple heads. Okay, but you do know that each packet, how many bytes you have, right? And in this way, you can say, hey, if I send one blue packet, then I send maybe 100 bytes, okay, and then I should send 25 bytes, 25 bytes, 25 bytes, still less than 100, but I can continue sending the fourth 25 bytes, and then I find, hey, now this catch up, then I send another blue. Okay, so this is the intuition. So you can accumulate the size of each flow. Okay. And so here we are doing the bit-by-bit round robin, but it's in a proxy manner. We are still sending in the packet way. Okay. So this is called the fair queue method, right? So the fair queuing. Okay. So we define a flow system where flows are served bit by bit. Then we serve packets increasing order of the deadlines, right? So what we do is we regard the sending as if it's by bits, but we have to take the actions in the unit of packets. This is what I just described earlier. Right? So advantage is that the flow will receive exactly its fair rate. So your packet size doesn't impact the bandwidth you occupy. Okay, everyone is still using fair. Okay, so this FQ achieves so-called a max mean fairness. Right? So the mean means, hey, you have 10 flows. What's the most unfair flow, right? So disadvantaged flow, the minimum bandwidth flow utilized, right? The one that's most disadvantaged flow, so the bandwidth to be maximized. Right? So this is you are not like a bully a particular flow. Okay. So here, let's take a look at the balancing fairness and utilization concept. Right? So assume that each queue gets to send X bits each round time. Right? So here, so assume you are doing bit by bit. Right? So what you will do is you will send you will send this, and then you send maybe by this time it's close to the blue side. Right? You will send another packet. Okay. And this is fair and a high utilization, right? So you are not sending two blue packets together. Okay. But here, the problem is that if you look at here, right? So let me see. When you send this, how to say this? So on the other hand, if you have this, right? So this one is ideal. Okay, it's fair and it's high utilization. Okay, but what if the second queue is not full? Right? It doesn't have enough packets. Right? So if you always have enough packets, this solution is perfect. Right? You just count how many bits you have, and always let the cumulative minimum bit queue to send, right? And keep doing that. It's like a merge sort algorithm where you have the position hat. Okay. But this assumes that you have enough data to send. Right? But sometimes, you know, the interaction of a particular connection is really not frequent. Right? You don't have too many packets. Okay? So in that case, if you want a fairness, right, even though by this time you are not utilizing some of the bandwidth, you should allow the blue packet, the second blue packet to send. Right? But because I want to execute the fairness, right? So because there's not much gray stream sending, right? So you should not send the blue frame. Right? So in that way, the bandwidth is idle while we still have something to send. Right? You should utilize that bandwidth to send the blue packet because there's no more gray packet to send. Okay. So here, in this case, capacity is wasted. Right? It's an idea. We should allow the blue packet to utilize this wasted packet. Okay. So here we are executing the so-called max mean fairness. Right? So if I parties request from results mu, okay, each will assume we each will receive mu I, okay. But here what we want is this, right? So the logic is like this, right? So firstly, cancel out those flows where you don't need to utilize too many bandwidths, okay. So like I don't have too much things to send. You think about the two groups of flows, okay. Some flows are sending very infrequently. You don't have too much things to send. Okay, so then you can allow them to fully utilize the bandwidth. Right, so you can send all the packets you have. Okay, but in the meanwhile, you also have some streams where you have tons of data to send. You can never finish sending. Right? You have a movie of 10 GB, for example, right? So then you should not allow it to go ahead and utilize all the bandwidth of the link. Right? You should cut off some of it. Okay. So think about the intuition first. Okay, so what will be your solution? The solution that, hey, so for those like infrequent packets, right? So we just let them send as much as they want, okay? Because they don't utilize too much bandwidth anyway. Okay. Then if we deduct the total bandwidth of the link with those that is occupied, okay? So for the rest, okay, it should be evenly split among these two streams. Each use 1/3 of it. Okay, so this using this share, this using this share, this using this share. Okay, so this is the intuition of this results allocation, right? Bandwidth allocation. But let's take a look at how this is achieved. Right? So more formally. Okay, so we say we want to achieve so-called a max mean fairness, right? So the allocation is max mean fair if and only if there's 3 requirements. No user receive more than its request, right? So this is because, you know, as I said, if I only have 2 packets, I just send 2 packets. Right? If you allocate 4 packets total, then I will be wasting these 2 quotas. I should allow other people to use it because I don't have more packets to send. Okay? So the second criteria is that no other allocation that satisfying 1, okay, has a higher minimum allocation. Right? So this means let me see, no other allocations. So this means because we have different ways of allocation, right? We want to find the unique allocation that is min-max fit, right? If you have another way of allocating it, right? And that particular allocation method to different streams with mu I has even a higher minimum allocation, right? So then this is not good, right? As we said, we want the minimum allocation to be maximized, okay? Right, so max min. So the most disadvantaged flow we should try to maximize its bandwidth. Okay, bandwidth. And finally, condition 2 should remain true recursively, which means now that if we remove the minimum user, which means now we already fully take care of that most disadvantaged people, right? We try to maximize it. After removing it, and it's used the bandwidth for the remaining bandwidth and the remaining users, right? This still holds recursively, which means for the second, most disadvantaged user, right? It's still, you take care of it. So this is, so after we reduce the allocation of the results for the most disadvantaged user, well, we try to maximize its use. Okay. So how is this idea actually implemented? Okay. So here, let's look at this formula. So how to calculate the maximum fairness. So here we have 4 variables. The first variable is the total link capacity. Right? So basically all the streams, right, sending speed, sum up to no more than C. Okay, that's all the capacity can use. Right? And so assume we have n flows, n streams going through this link. Okay, and so when I send through this link, everyone will have a desired bandwidth of flow. Right? I want to send at that particular speed. Right? But then you will get back a speed. Right? So that sending speed will not be more than your request. Okay, you will get mu I, which is either Ri if you are not sending too fast, or mu I, which cut off your desired sending speed. Okay, you should not go beyond that. So F is so-called fair share bandwidth. Right? So that's where this is, hey, if you are sending you have too many data to send, and you request too many bandwidths, right? I only give you F. That's maximum loss. So you can see that, for example, for the I stream, we have n flows, right? We have n flows, okay? For the ice flow, particular flow, right? It's allow the sending speed is how much you request, right? If you are not requesting too much, right? You are sending not frequently. Fine, I give you this. Right? But if you are more than what I can allow, the max allowed for some user, right? Then the M will take effect because Ri is larger than F, and min is this equal to F. Okay. Well, any questions? So here we are making sure each flow can receive most of the fair rate, which is min Ri. Okay. For simply the intuition that if your Ri is not too high, I can just if you request how much bandwidth, certify you how much bandwidth. But if you request too many, right? So then I cut off by F. You cannot go beyond, right? Which is the fair rate. And this F is computed based on the current saturation and the fairness, how many flows you have. Okay? So here's an example. Like we assume that we have 3 flows through this bottlenecking. The first flow, we request a bandwidth of 8 packets per unit, per time unit. And the second flow want to send using the grid, right? 6 packets per time unit. The third request only 2 because it doesn't have too much to send, right? And if you look at this, right? So this is more than 10. Let's say each time unit you can send a 10 packet of 10 bits, right? So if you sum them up, it's 16. Right? Go beyond the 10. in that case, we cannot just let them go, right? So we need to back up some of them, okay? So how can we compute this, right? So firstly, what we do is, now we have 3 flows, and totally they can sum up to 10. What's the average flow size that it allows, right? So the average is 10 divided by 3, which is 3.33, okay? Now that we know, hey, 2, right? This one is even lower than the average allowed, right? It's not using more. If you think about everyone has tons of things to send, then everyone should use 3.33, okay? But here, apparently, this guy is using less than average. Right? We should just satisfy this case, okay? So if it requests 2, it will send 2. Now, the other 2, 8 and 6 are all above the average, right? So what we can do is, now, 10 minus 2 is 8, right? We have still 8 bandwidths that can be shared by these 2, right? Okay? What we do is we will compute, right? We still have a capacity of 8, but we have 2 flows to satisfy. What's the average? Right? It's 4, okay? And 4 is what is allowed, right? Because, we allow 4 and 8 and 6 each are larger than 4. Okay, so what will happen is we allow each other to send. Right? So you can see this is actually a recursive algorithm, because what if this is not 8 and 6, right? What if the rest is 8, but you have 2 numbers and one of them is going below the average, right? And then you can again satisfy this and then consider the rest. Okay, so this process can be recursively done. But anyways, the solution is after kicking out those disadvantaged ones, then you have the remaining bandwidth, right? And you divide by the remaining flows, right? And you compute the average. And those that go below the average, you should satisfy them totally. Okay, and above the average, you just allow them to use the average. Okay, so that's the idea. Any questions? Right. So let's think about why this method is good. Right. So think about, compare with, we allow everyone to use 3.33. Right. Now this guy only has 2 to send. There's 1.33 that is not utilized. Okay. Then they can be distributed to them, and they can send in a little bit higher speed than 3.3. Okay, that's the idea. Right. So this is the intuition. So if you look at the way of calculation, right, so this is below average, so it's 2, we allow 2. Right? And then these 4, then because they are large enough, we cut off that. So how to implement this fair queuing method in practice? Right? So we can do preemptive scheduling when packets are on bit-by-bit basis. Right? So, but this is ideal case. Right? So we are not operating on the bit-by-bit case. Right? So we can only do so-called practical estimation. Right? We still packets in the order that they would have finished the transmission in the flow system. Right? So basically, we assume the packets are sent in the unit of bits. Right? If that's the case, what's the ending time of each bit? Right? And then we look at the packet boundaries and say the last bit should go out when. And we follow that order of the deadline. Okay? And then we order the packets. We use bits to complete the deadline, and then we order the sending order of the packets using the boundary bits. That's the idea. But here's an example. Assume we have flow 1, 2, 3, 4, 5, 6 a long time, and the flow 1 is sending a little bit faster, right, earlier. And flow 2 is sending, and they have a lot of packets to send. So what will happen is if you flatten them into bits, right, and consider fairness, right? So basically, you can send, this packet is equal to 2 packets here. Right? You can send something like this, okay? But actually, when you send, you will do something like this, right? You send a 6 in its entirety, and then you send 5. You cannot send half of a 5, so you have to send 5 in its entirety. If you send this and you kind of disadvantage the first flow, then this 5 should be sent. After that, it's even again. You send these 2 flows. And after you send this 4 in its entirety, then the deadline of 3 is kind of delayed. So you should immediately send 3. Okay, so this is basically the idea. Right? So you still send the unit packet, but we complete the deadline in bits. All right, so here's a simulation example, right? So if we have a bandwidth of 10 Mbps, right? And if we just use a random early detection, right? So we don't use a fair queuing solution, right? Then you will have this will happen. Right? So the UDP is using all the bandwidth, okay? And the TCP is using, it does not have too much to do, right? Because we are not cutting UDP's bandwidth. Right? So here fair queuing, if you want 10, I only allow you 4, okay? 8 come and 4 come out, right? Even if you are sending crazy, I have a cap for you, but you will not send it beyond. Right? So keep in mind here, the scale is different. This is using 8, okay, MBPS. This is using 4, 0.4. Right? Okay, so it looks like the bar is the same height, but it's different. Okay. All right, so let's take a look at here. So if you enable fair queuing, even though UDP is still more aggressive, it will be slightly higher, but it will not utilize 8, right? It will only utilize 0.4. Allow the others to also utilize some bandwidth. So the TCP connection can smoothly go through, even though you have a UDP that is pretty sensitive. Okay. And usually, maybe you also want a UDP, application level, like YouTube server may find, hey, I lose so many packets, right? So the user has some feedback, maybe also in UDP. I should do something. So I should send it slower. Okay. Maybe there's also some magnitude. And so there's also a problem here. So fair queuing requires per flow state in the router. If you remember, we need to keep a record of how many bits are cumulative send, and we need to calculate the deadline. Right, we need to maintain the flow state, basically source, destination, IP, and port. Okay, and then the state, how much bits has been sent. Okay, but you never want a per flow state in the router. Okay, right. So the fair queuing is actually, in reality, we're not actually implementing this idea. Right? So we are approximating this idea using so-called a core stateless fair queuing. So you can see we try to eliminate the state. Okay, and this is done at least in some of the routers. But if you have the end router, that's fine. Right? So in the core router, in the internet backbone, and then this is affordable because if it's an ISP serving like 2 big regions, right? So from East Coast to West Coast, there are so many connections, so many stuff there, right? If you maintain the states, it will be created. Okay. So what the idea here is for CSFQ, like stateless, right? So is that we have a contiguous and a trusted region of the network, right? So each router perform per flow of ad routers, like those ad routers connecting to these hosts, right, will perform per flow operations, like fair queuing that we mentioned before. But the core routers don't want to, like these in the middle, right? So don't want to take these expensive state maintenance. Okay, so there's no per flow operation. So this is fair queuing everywhere. Yes, because these are the edge routers, but the core routers not serving the edge should not maintain the state. Okay. So there are algorithms to achieve that, which we will not go into the detail, but gives some idea. So if each packet of flow with arrival rate R is forwarded to this probability, right, with this probability. Right? So this is F is a fair rate, okay. But you also monitor arrival rate, okay, and you basically you have a probability control, right? So the mean is to guarantee the probability don't go beyond 100%. But if your arrival rate is too fast, right? So we will reduce the fair rate, okay? And again, so keep in mind, this is the packet drop probability, forward probability. Right? So we will, if your arrival rate is too high, the forward probability will be dropped, and the drop probability will be increased. Okay, then you effectively control the flow sending speed. Okay? And here we have a simple calculation here. Right? So if you have another forward speed, right? So how do you calculate this? Right? So if you have a sending rate R, and the algorithm in the core router says, hey, I want to compute this P in this way. Right? So if you time R with this P, which is this thing, right? So you left-hand side gets R, right-hand side gets, okay? So this exactly recovers the R prime, which is what we want. Right? So we want an average flow to send in a bandwidth like this. Okay. But the problem is that we, in the call router, we don't have the state. We cannot do this. Right? So what we do is we just monitor the arrival rate, and our job probability is computed according to how fast your packet arrives. Okay, we don't need to maintain that packet state, and we can still approximate the same fairness requirement for fair input. Okay, so there's no need to maintain per flow state. But the important thing is, how do you know the arrival rate, right? So because if you need to know the arrival rate of a particular flow, right? So you still need to say, hey, you have this flow, and this flow. Hey, for a time unit, I get 3 of them. I get 1 of them. Right? You need to maintain the arrival rate, right? Then you need to still keep the flow. So in order to address this concern, right? In here, the rate is actually carried in the packet. Right? So the call router just checks the packet. The packet itself tells you, hey, how fast I'm arriving, okay? Because the edge router will know how fast it's sending. It will send this data into the packet. Okay? Then you can read it. And once you read this information, you can calculate, because this value is here, the fair rate you know. Okay? You can calculate it, right? And then you forward with this probability. Right? And if you really unfold it, right, with the true R, it's really, you have the fair queuing criteria satisfied. But you don't need the state. The edge router needs to like put the sending rate into this packet. Okay, so the outline of the CSFQ algorithm is as follows. Right? So you have the ingress router, you estimate R and insert to the packet header. Right? And the call router is just to compute the R, okay, because you have the R in the packet, okay, compute the fair rate. And then here you don't need the state. You can compute the fair rate based on the, because you have the allocated bandwidth to everything, right? You know whether it's below average or not, okay? And then you can compute the F, okay, like what we see before, like 4, right? 8 divided by 2, okay? And then you include the packet with this probability, where R is obtained from each packet, okay? And you will update the packet label, right? Because when you send, right, you may cut off by F. Right? R prime could be R, but it can also be F, right? If R is larger than F. Okay? So if this changes, you need to update your packet's sending speed to be the new speed, which could become slower. Okay. So the egress router is where the destination to the destination host, the last router. Okay. Then we'll remove this extra state. But these state are, so the R is only maintained between the routers, between the hosts. You still see this IP packet. You don't see this rate information. Okay. Here's an example. We maintain the per flow state, and we insert R to the header. Right, so we have a rate. Okay. And we write the call, and we may update the rate. Okay, maybe now we should back off a little bit, right, because the fair rate is F is low. Okay. And then we send to equal. And the application need to remove it. Okay. Let me see. I think time is up. We'll continue next time. So the next class is the last class before we review, right? So, and what we will do is we will have another topic, right? So, and that topic, after that topic, we will basically these are all things that will be covered by the file. Okay, and we have still 3 to 4 slides. We will continue in the next time. Okay, any questions? Yeah, today we didn't take attendance, right? So maybe next class we will take attendance, or the Friday's class.
I'm so glad.
Hello? Yeah, if you have no question, then that's the end of the class, and have a good day. So these things are, we may test you in the final exam. Let's say we will give you an example. You need to compute the fair rate, just like the previous example. Okay, but we will do it in the multiple choice manner. Okay. Okay, so in that case, I will see you on Wednesday, and I will upload the video to YouTube and send it. Thank you.